This conference will now be recorded.
Okay. And for those who don't know, I really benefited from Giuseppe when he was in Reading, and he was a senior research associate with me for about 5 years. That was really great, and I'll show quite a bit of that work as well. So this is really about, I'm assuming that you have a bit of a mixed background in terms of storylines. Some of you may have heard of it, some of you maybe not. So I use this somewhat provocative title because, in fact, it's becoming kind of a trend almost. And in Germany in particular, there are all these projects doing storylines. I'm not always convinced that everybody who's doing storylines, once something catches on, it's good to go back and ask yourself, well, why are you actually doing this? So I thought that's the purpose of this. So I actually start with a study in contrast. So 20 years ago, there was a heat wave in Western Europe, and sorry, see, this is a problem. I should have. You see all my meetings. That caused 70,000 deaths in France and so on. And there were two papers after that analyzed. So one was from the Meteorology department at Reading, five authors, including Brian Osmond's. Emily Black was the lead author. It was a very detailed analysis, essentially a forensic analysis of all the causal factors that played a role. And they talked about the persistent anticyclone, the SST anomalies drawing the land surface, and so on. And they concluded it is not known at that time why the large-scale circulation had the character it did. But they made the point that the large-scale circulation was crucial for the heat wave. One on the right was by Stott et al., and they ignored all those factors deliberately. I mean, they explicitly said that. They targeted a much weaker, coarse-grained event. I say quote-unquote event because it was over all of Western Europe. I think it was the entire summer, as I recall. And the event, the heat wave, was 1.6 degrees above the mean. Nobody dies from 1.6 degrees above the mean, do they? They had all sorts of statistical arguments to avoid selection bias, and this has become, I mean, Black is a highly cited paper, but Stott has become the dominant paradigm. But actually, this paper is an early, I would say, an example of a storyline approach. So this is the, I led a paper from a workshop of about 20 people, and we published this, and this has become sort of a reference, I guess. And the definition we used there was storylines were physically based on foldings of past weather, climate events, or plausible future events or pathways. So it was deliberately phrased to include past and future, to include events as well as trends, to be quite general. I think some people find that confusing. I like to unify. I guess there are people that like to unify and people that like to sort and fragment, so I'm one of the unifiers. So a version of this is now in the IPCC glossary, and this was the, in the paper we had an example. This was from Bologna March, a Swiss scientist, and she talked about an event, a rain on snow event that led to quite high severe impacts. So what happened in the autumn, there was a cold front that came through. It dropped a meter of snow, and then a warm front came through. There was an atmospheric river tucked behind it. It had a rain on snow event. Then there was on the right here, there was a local, what's called a cedar feeder circulation. So it's a very local phenomenon. They have measurements across the valley. You can see that it was very different on the upwind and the downwind part of the valley. It was not forecast because weather forecast models are not high enough resolution to model this, or at least weren't at the time, but it's a well understood meteorological phenomenon. It led to mudslides, it closed off a valley, and there was a lot of concern about that. So it illustrated the different, in this paper we talked about the different topologies of use and gave examples. So it's not that storylines is anything new, we were just trying to put a name onto something that was already there in literature, and if you like, raised the epistemic credibility. I've been most interested in the partitioning uncertainty part, but there's others that work more on these other aspects. So this is a motivation from work that Giuseppe did when he was at Reading. So one of the motivations, if you want, is just the fact that if you talk about precipitation change around the world, this is mean precipitation change, there's a lot of uncertainty. This is a classic IPCC map of changes by the end of the century under our CP 3.5. And if you do this for temperature, it warms everywhere. Maybe there's a little patch in the North Atlantic that doesn't necessarily, maybe there's a bits of the Southern Ocean, but in general, over land for sure, it warms everywhere. But for precipitation, as you probably know, it isn't the case because precipitation can go up or down. So this was a stippling that Giuseppe came up with that we were hoping IPCC might adopt for the AR6, but they thought it was too complicated. So the black is the classic IPCC stippling, where at least 90% of the models agree on the sign of change. And we introduced this open stippling. And that's cases where the models show responses individually that are beyond what you get from internal variability, but they're of different signs, so it's not a robust projection. And just to illustrate, for example, if you look at Singapore, over here, it's on the boundary, but there's most of the models show a drying, but some models show a wetting, and some show a very strong drying. And again, this range is outside what you would get from just internal variability. And then Sub-Pol is the opposite. It's just on the boundary now, but a tendency towards wetting, but some models can give a lot of wetting, and some can even get drying. So why is this? Well, the first reason is that dynamics is inherently chaotic, the butterfly effect, if you like, and that leads to substantial internal variability. When you look at the response to a forcing, the signal-to-noise ratio of the forcing is comparatively small compared to thermodynamic aspects of change. So this is a paper from Claire Desser a little over 10 years ago now. It was one of the early versions of large ensembles, single model large ensembles, which have now become much more standard. This was one of the first. This was PDFs or histograms, I should say, of. So these are wintertime trends from 2005 to 2060, so 55 years in the Eurasian North Atlantic sector. So it's a big region. On the right, maybe start with the right, there's surface air temperature. I've forgotten how many are in the ensemble, but it was around 50, I think. So the histogram in gray is the control run without climate change, and you see that some of the simulations show a warming, some show a cooling, but on average they show 0, as you expect in sampling. But if you look at the red bar, that's the runs with climate change, and they all show a warming. And although there's a little bit of overlap, there's not much. So you can see that the average warming is about 3.5 degrees or something. Or sorry, this is standard deviations, 3.5 standard deviations. But if you had a single, this is the model with 50 realizations or so. The real world has one realization. If you have a single realization on the right-hand side, you'll be able to tell if it's in the gray band or the red band. On the left, we have the sea level pressure, which is a measure of the atmospheric circulation. And here you see that it's a different picture. There is a change. It's certainly statistically significant. The shift is about 1 standard deviation, and we have a lot of sample sizes, so there's no doubt that in the model, there's a shift of this index, the sea level pressure. But you can see that they're very overlapping, and a single realization, you probably wouldn't be able to tell if you're in the gray one or the red one with any confidence. And then if you look in the middle, that's precipitation. And it looks a lot more like sea level pressure, just with a sign inversion than like temperature. So in the winter, no surprise to you, in the winter, over the Eurasian North Atlantic sector, precipitation is controlled much more by dynamics than by temperature. It's the position of the storm track. Now you might say, people have said to me, well, so if you can't tell from a single realization if you're in the climate change ensemble or the no climate change ensemble, maybe it isn't important. But in fact, if you look at these shoulders, not even the tail, you've got about a factor of 2 change on each side. So you've got a factor of 2 change in dress, which is big change, which is essentially undetectable. That's the kind of problem that we're facing. And to make it worse, that's a single model, but the models give different answers. And so this is an example from 10 years ago, and these are the SEMA 5 models at the time. They had some small ensembles. Some of the models had small ensembles, so there's stippling, which indicates where for each model, we are confident in the response. This is the response of the near surface winds. The gray is the climatology, so that's the bottom of the jet stream, and then you have the positive or negative wind speed changes, and these are 4 different models. And you see that they give a very different pattern. So, the reds and the blues are, apart from North Africa over Europe itself, the reds and the blues are in different places in opposite signs. This is also, I guess, because of chaos, because, I mean, I wouldn't want to make this too tight a connection, but in a chaotic system, if you change parameters a small amount, the attractor can change a lot. So you get a big change in climate from small changes. And we know there's a lot of sensitivities with boundary drag, with gravity drag. Models can be, especially for the jet stream, the climatologies can flip around. Obviously, every model says something's going to happen. If you average it, you get not much of anything, but that's not the most likely outcome. The other thing that's a bit more, let's say, philosophical is that climate circulation-related climate model, climate phenomena, they're very real, of course, jet streams, storm tracks, etc. But they're subjectively defined. We had a workshop, you were probably there at the time, Giuseppe, on blocking and Reading, all these experts on blocking, and there was an idea to try to come up with a definition. It didn't work, because every expert had their own definition. And that's the way it is. It's the same with storm tracks. And it's because they're emergent phenomena. They emerge, they don't follow directly. You can't look at the Navier-Stokes equations and figure out that you're going to get a great red spot. It just isn't obvious. So in contrast to thermodynamic quantities, they're basically extensive. So if you double the size of your box, you get twice as much energy and so on. These are extensive. But dynamical quantities, they're not extensive. If you double the width, you don't get twice a jet stream, right? The jet stream is where it is. So you can't aggregate in the same way that you can with thermodynamics. And a lot of people work with energy budgets, and you just take a bigger box, and you get a better estimate of the energy budget. The fluxes become less important than the internal quantities. But with dynamics, you can't do that. So you can't spatially aggregate, which is the usual way to beat down the noise or simplify theory. And generally, many mechanisms play out differently in different situations. I find this almost amusing. I don't know if anybody in the room was involved in this annex, but the IPCC and the AR6 had this annex about monsoons, and they drew this picture, and then there's all this text. But they don't, they say, well, Southern Africa, that's not really a monsoon, so we won't talk about it. Equatorial America, that's not really a monsoon, so we won't talk about it. I mean, really? This is like very bizarre. And you have to come up, I'm sure they wanted a definition, and then it's got to do usually with the reversal of the winds. A lot the definitions have tended to come from the Indian monsoon, because that's sort of classic. But that's specific to India, and the different continental, the different mountain ranges, different oceans mean that the monsoons play out differently in different regions. WCRP has monsoons everywhere. Now, in IPCC, the uncertainty about dynamical quantities, I said that you can't aggregate, but there's one thing that you can often do, and that's take the zonal average. So what's happened, if you look at the statements about the dynamical quantities like jet streams, they tend to be statements about the zonal average. And generalization can be locally misleading, and this is from a paper by Julia Midland, who was a PhD student of mine in Argentina. She's now in Leipzig. She was looking at the southern hemisphere, and the southern annual mode is a major climate variability mode that affects the precipitation over the middle latitudes. And people have talked a lot about what the SAM does, and this is just the SAM can respond though to changes in the stratospheric polar vortex or changes in the tropic warming. And in fact, if you want to look at precipitation, these are for the same sign of SAM change, but these are the SAM changes induced from the tropics, and these are the SAM changes induced by the stratosphere, and they give completely opposite sign in terms of the precipitation response. This is a weakness of generalization. Because the SAM can change either from a strengthening of the westerlies or from a shift, a forward shift, and they have very different effects. This comes up a lot. So the regional scale, when you take a traditional approach to this, is another point, the long-term changes. Again, if you do this for heat waves, you get a pretty uniform map. But this is for drought, and it's actually specifically agricultural or ecological drought, which is soil moisture-driven drought. So it's actually the drought that's affected most by temperature. If it was hydrological drought or meteorological drought, it would be harder. This is the easy case, I guess. But so this was a map produced in the summary for policymakers, and they divided the world into these boxes or hexagons, and then the beige is where there's an increase in drought that's been observed and attributed to climate change. There's one region, northern Australia, where it's a decrease, but you normally expect increase. But you see that large parts of the world, there's low agreement in the type of change, just as I showed from Giuseppe's paper early on, that you can get different signs of the response, and in some cases, limited literature. But interestingly enough, if you go into the IPCC, into the AR6, into chapter 10, which is sort of a storyline chapter in a way, there's a lot of information, especially about regions that actually are hatched or gray in here. It's just that the information is expressed in conditional form. So they know that there was a change in drought, and they know it was linked to changes in sea surface temperature patterns. They just can't attribute the changes in sea surface temperature patterns. And because IPCC insists on an unconditional attribution, they can't say it. But if you allow yourself to attribute it to SST patterns, then you have a bit more freedom. Now, we actually have a huge amount of climate information. There's this idea that the uncertainty grows as you go to small scales, but I think that's, in a way, fundamentally wrong. It's just that the information is conditional. So I mentioned the French heat wave early on. This is a paper that I really like on that. So this is a box, 3 kilometers squared in central France, and the left column is one day in this is observations, one day in August 2000 with no heat wave, and right-hand side is one day in August 2003 with a heat wave. The top image is the vegetation index, so red is living and green is dead. And you can see that this is a forest, which is still there. There's some hedgerows, which are still there. And then you have a lot of the pastures and fields where the vegetation has died out. There's a few cases where there wasn't any, it was bare there. But, so you have a lot of information. And this is the temperature, surface temperature. Now you would say that you can't compare temperature on one day in 1 year with 1 day in another year because of weather variability. And that's true. The absolute difference could be just a variability. But the precision across this scene, because this is 3 kilometers, and weather variability is much larger scale. And you see that in the forest, it was only 11 degrees warmer, but over the open area, it was 20 degrees warmer. And if you isolate and leave out the hedgerows, it's 24 degrees warmer. So this is tremendous signal to noise. You've got contrast over 50 meters, and you can model these processes with land surface and forest. You can feel it, you can measure it. So we may not be able to predict the statistics of heat waves in the future, but we can predict the implications and how to manage them. So that's one of the motivations for it. But it's because of conditional information. And then there's cases where even if the sign is correct, so all the models agree on warming, but the magnitudes can be quite different, and the observed trends can lie outside of what the climate models can do. This was a paper by Cotard et al. 2 years ago, pointed out that in France, the summer maximum of daily maximum temperature has been increasing since 1950 up to 5 times faster than the global mean. Now, part of that is, of course, you don't expect land always warms more than the global mean, and the summer is going to warm a lot when you dry out the surfaces. So two-thirds of that is understandable from the thermodynamic processes, but a third of it is due to the dynamical trends, which they link to Atlantic sea surface temperatures, I believe. And they're not present in any model, even allowing for internal variability. So that kind of leaves you with Well, maybe the models underestimate the variability. In fact, we know they do. In the Atlantic, the decadal variability is much too white. It's not red enough in various observations. That's been well documented. So you can certainly argue the models probably underestimate variability. Maybe if we had a more realistic variability, maybe then the observations would lie within the model range. If that's the case, then actually we expect, if it really is variability, at some point we'll get regression to the mean, and this trend is going to come back down again. But maybe the dynamical trend is forced, and the models are just missing it. I'm not actually aware of a specific theory for that, but somebody might have one. And those are both plausible causal explanations. So we have a lot of uncertainty even for things like temperatures. So I think the heart of the problem is that scientists are pressured to issue single definitive statements. IPCC wants a single definitive statement typically. Journals want a single definitive statement. A lot of titles of the so-called high-profile journals are really statements. This caused that, not something like on the understanding of something fuzzy. They want a, declarative statement. That works perfectly fine for thermodynamic aspects of climate change, but for dynamic aspects, if you really insist on a single definitive statement, you wind up with something that's reliable but rather uninformative. So what the AR6 said about storm tracks in the North Atlantic was that there was low confidence in the projected changes. That's a reliable statement, all right, but it's not too helpful. So Sterling argued in this paper it wasn't about climate change, it was just about science in general. We need a language for expressing a plural conditional state of knowledge. And I had this image from, it's actually a book on decision making under deep uncertainty. And they talk about these different levels of uncertainty. And I think, IPCC would like a best estimate with an error bar or whatever. And the storylines are trying to be out in this space where we can't put a probability around what we're doing. Now, I'll give an example of an event, Hurricane Sandy, which was a tropical cyclone that hit New York City or close by. It wasn't unusual for most of its life. It just took a very rapid westward turn at the end of its life, and it then collided with an extratropical storm. Both of those were the result of a strongly deformed jet stream. And it seems almost so it's like two bullets flying in the air. We certainly don't have any expectation of how deformations in the jet stream are going to change. I mean, there are some wave vortex arguments, but especially this time of year, I don't think anyone would claim any strong theory there, and certainly no confidence. So it seems almost meaningless to ask if such a fluke event would become more likely in the future. But we do know that sea levels will be higher. We do know that the atmosphere will hold more moisture. So you can ask and possibly answer these counterfactual questions. Given Sandy, how much would the impacts increase by climate change, or how much worse might they be in the future? So you consider Sandy is given, but you say the storm surge that flooded the subway system in New York City was this much higher because of climate change. You can do that kind of a calculation. And if you look at most extreme events, actually the role of dynamical conditions is usually very important. I mentioned it for the French heat wave and in the Black and White paper. This is an example of a wildfire analysis from scientists from the Australian Bureau of Meteorology. So this was a wildfire season of 2019. They have frequent now bad wildfire seasons. They have a statistical model just based on regression of what's called the fire risk index. So this is it's an operational index used by the firefighters and emergency planners to deal with risk. It's what we would call a climatic impact driver. It's an index which is based on and you can see that this was the observed fire risk index, and this was what they get from their statistical model. It doesn't work, but the area of interest is the eastern part. And if you recompute the contributions to that total, the long-term trend in warming is a very most coming from seasonal drivers. And there's three in particular. So there's the Pacific sea surface temperature patterns, the Indian Ocean sea surface temperature, polar vortex. So those different dynamical drivers led to the drying, which was the key factor in the fire risk being high. And we don't know how those are going to respond to climate change. They certainly will, but there's a lot of uncertainty, and generally people just focus on the warming part. So if we could address this would be very helpful. So the storyline approach is really a conditional attribution, and this was a recent. I've been working with philosopher of science Lisa Lloyd for a few years now. This was a paper we published a few years ago, and we're trying to find a framework for this in the attribution space. So the idea is that you have some target quantity that you're worried about. Let's say it's a fire risk index or something, and then you have an external driver, which actually in the IPCC, this is the IPCC language, but it could mean something like a blocking anticyclone or some local circulation pattern. And so it could be like in here, and then this will be driven by, let's say, SST patterns. So this thing, so you've got the storyline kind of like for Sandy, where you take the local circulation as given, and then you just ask how much sea level or moisture or something like that. Or there could be other known forcings like volcanoes or something. And that local circulation feature could have a driver from, let's say, sea surface temperature patterns, as well as perhaps directly anthropogenic climate change or some other known forcing. And that SST pattern itself could, of course, have climate change and so on. So you work backwards, and there's uncertainty at every step, but you're partitioning the uncertainty. And it's completely consistent with the IPCC DNA guidance paper, but in the IPCC, the working group one has not been happy with conditional explanations. They've always wanted unconditional, but working group two is much more comfortable with conditional. And of course, it's standard practice in other areas like seasonal prediction. So I think it's actually quite orthodox climate science. There's also the narrative aspect, which is not so much the bit that I focus on, but just to mention, in passing, the storylines provide the basis for interpretable climate risk narratives. And Chris Jack, who works in Cape Town, has get example here where they're dealing with a local community, a city in Namibia, and talk about they boil down climate features into much hotter with a drier rainy season, hotter with rainfall late in the season, warmer with a summer rainy season. The idea is that the storylines can give you self-consistent aspects of compound risks. Okay, so there's two main kinds of storylines that have been used so far. This was based. This was a figure in the IPCC based on a paper of mine a little bit earlier. Just expanding a little bit. So the idea is that you have you work from the upstream end. You have greenhouse gas emissions. You have climate sensitivity, which is how much the climate system warms for a given CO2 level. That leads to a certain global warming. That will lead to regional warming patterns, which are quite well understood. The fact that land warms more than ocean, the fact that the Arctic warms more than the lower latitudes, and so on. But then you've got remote drivers like SST patterns, or the stratospheric polar vortex, or something like that. That will lead to the dynamical conditions, and these will combine then the dynamics and the thermodynamics essentially combine to give you a hazard, and that of course will then lead to impacts. And you can work also on this vulnerability and exposure part of it. So when you specify a global warming level and a driver, you're basically changing the nature of the question. These are dynamical storylines or circulation driver storylines. So now when you condition on a global warming level, you don't care about climate sensitivity anymore. Climate sensitivity matters for people worried about the carbon budget, because this is what's known as a causal network, and when you condition on a factor, you basically block the rest of the diagram. So now you introduce that climate sensitivity affects how much greenhouse gas emissions you will be allowed for a certain global warming level. And from the adaptation point of view, you then just give it a global warming level, and you can then say what happens under these different drivers. So another paper from Zebby, which you did in writing, is I think the first example of this kind of approach. And the idea is that you can partition the uncertainty in the circulation from these large drivers. And these are drivers that are fundamental parts of the feedbacks of the climate system. So this is the polar amplification. So we know that the Arctic warming is amplified. There's a lot of uncertainty in that in models because of the boundary layer processes and mixed phase clouds and so on, and ice treatment of ice, but it's a fundamental process, and the models disagree on the amount of amplification. And you also tropical amplification, that's the upper troposphere amplifies warming compared to the surface. Again, models have a wide range of there because of convection schemes and things like that. Then you have the stratospheric polar vortex, where the models give very different answers, basically because of gravity wave drag is the main uncertainty. So you've got physical parameterizations that are known to be uncertain and lead to a large spread. The models give a large spread, but then we also know from seasonal prediction and from model intervention experiments how these different drivers affect, let's say, Europe through teleconnections. And that's the idea. You get these teleconnection patterns, which are shown here in terms of the lower tropospheric zonal wind in the northern winter. So you see that the polar amplification is pushing the jets equatorward, and the tropical amplification and the vortex. This is a stronger vortex case, are pushing it poleward, but in different ways for the different drivers. So because we have multiple lines of evidence, as I say, for model intervention, it's a regression across models which you wouldn't trust on its own, I think, but because you've got all these different lines of evidence, it's clear. So here's another example with Rohit Ghosh, who was a postdoc, and this is just so as not to show too much of Giuseppe's work. This is the maritime continent, boreal summer, and you see the precipitation changes there can be different in sign over many of the regions. So Rohit had, in his case, he just had two drivers. One was the basin-wide equatorial Pacific SST, the BEP, and then the other was the difference between the west and the east. And you see that they give very different patterns. And in particular, if you look at the observed trend over more than 100 years, this is the basin-wide warming and the west versus east, especially this one, you can see the observations are down here, and the models are pretty much all to the left. So, and this is a well-known problem. There's been quite a literature on the fact that the east minus west SST gradient in the equatorial Pacific, the climate models just aren't capturing this at all. And there's actually many cases around the world, and Tiffany Shaw led a paper in Frontiers last part of the WCRP special collection on the Open Science Conference with many examples. Now, there's a growing number of examples like the Watara case as well, where you're getting trends that are outside of what the models seem capable of producing. So we have to be able to deal with, to have some guidance in how to deal with those cases. Now, I showed you before with the hexagons, these IPCC regions. They can be pretty bad regions, actually, and I guess they're chosen for all sorts of, political reasons and so on. So this was again from Julia Mindland, a paper a couple years ago. So she was looking at, she had storylines here of just focusing on southeastern South America, the regions shown here, and this is a multi-model ensemble mean for the summertime for precipitation changes, which is wetting everywhere. So this box A is the IPCC AR6 box, and there's other boxes that have been used in the literature. This shows the precipitation changes. So she had storylines based on these different drivers, including equatorial Pacific SSTs, and you won't follow all this, but if you just follow these different lines, you can see that the northern part of this cross-section, northeastern part of this cross-section, which is box F, a lot of the storylines change. So they're pretty coherent through here, and all of a sudden things change. So if you try to do a storyline analysis, you wind up with canceling effects across the domain. This is trying to reconstruct the spread in the climate models, which are shown in blue for the different regions. RR was just, I think, her version of Giuseppe's analysis, and then SL was something else that she did was trying to emulate a distribution in some way that was just a different way of trying to do the same thing. You can see that if you try to look at box X, the orange and the green are similar. They're pretty much capturing the blue. Same for E, same for D, same for C, same for B, but not for A. All of a sudden for A, it doesn't work at all, because A is including F, which is doing something very different from the rest. So, if you're creating some population, statistically, you should not involve things that are very different. This is called in English, in the English language literature, Simpson's paradox. And that's what you do if you include a box. So it can be used also to optimize boxes. The other kind of storyline that's been used is called an event storyline. So that's when you just move further along this chain and you condition on a regional warming pattern and you condition on dynamical conditions. And I forgot to mention it was written. You could bring a tipping point in here if you wanted to. No one's done that yet, but it's certainly possible. And here you think of perhaps some kind of a worst case event. So here's an example. Again, I also was a student at Hamburg, and she was using a global model. So what they did, this was a setup that they actually had developed for regional climate modeling a long time ago. And they nudged an atmospheric model spectrally, but just at the very large scale, so T21 spectral resolution, if you know what that means. And you just constrain the winds in the upper troposphere, and you let the whole lower part of the model respond. There are other ways that you can do this, and in regional modeling, it's called the pseudo-global warming method, where you impose the boundary conditions. But this was a spectral nudging. This was the case of the Russian heat wave in 2010, a very famous event. And the idea here is that you can, the factual is the event that did happen, and the red is the counterfactual without climate change, where you just change the SSTs and the greenhouse gases. And you see that even with 3 ensemble members, you get a very clear difference between with and without. So it's like the Sandy example I was talking about, where you would imagine the same tropical storm, but just with warmer conditions. Here you're assuming the same atmospheric circulation, just under warmer conditions. So there's a lot of benefits to this. You have a very high signal to noise ratio in space and time. You could drive an impact model. You can use much higher resolution models. But also it's a question of justice, so I'll finish with this aspect. Now, there's a very famous book called Small is Beautiful, which I'd heard about growing up, but I'd never read. Finally, I decided I should read this book. I think COVID, my kids are long left home and everything, so COVID was a very quiet time and I could do a lot of reading. So he had written this book in '73. He asked how economics would look if it was done as if people mattered. And so Regina Rodrigues, an oceanographer from Brazil, who I'm leading WCRP project with, I'll mention that shortly, we use this as a launching pad to think about, to ask Schumacher's question of climate science. How would climate science look if it was structured as if people mattered? And we pulled out 3 themes out of Schumacher's book that we could see, which are backed up with lots of quotes from him about economics, of course. The first is you cannot simplify the local situation. You have to deal with the local situation in its full complexity. And as we've seen with the forests in the French heat wave, the way you do that is by expressing the climate knowledge in conditional form. You could think in terms of expressing things in terms of conditional probabilities. That lets you retain the full richness of the local situation. On the other hand, you need a method which is simple. So you somehow have to not overcomplicate things. You're dealing with deep uncertainty. So physical climate storylines is a way we argue to keep things simple and yet complex, if you like. but also empowering local communities to make sense of their own situation. So as Schumacher was talking about engineering works and stuff like this, where you would build some waterworks in a developing country, and you would hire some company from Europe, and they would do something very fancy, and as soon as they left, it would break, and then they didn't have anything to work. So you need what he called intermediate technologies that can work at the local scale, and so it's intermediate between something very primitive and something that's state of the art. So in our case, we're talking about data science, and causal networks are a way to make sense of the data science, I think. So this was an example that we had in the paper Regina has published on this event. It was the failure of the monsoon, the South American monsoon in 2013-14. There was a blocking anticyclone shown here. This is the climatological precipitation where there's flow out of the Amazon in the convergence zone. There was a precipitation anomaly, very dry because of the blocking. You got high temperatures. The reservoirs dried out, the croplands dried out. There were marine heat waves, classic correlated risk, the food, water, energy nexus. There was a probabilistic study using these simplified kinds of treatments I've talked about, and their conclusion was it found insufficient evidence that climate change increased drought risk. The risk ratio is, if it's greater than 1, it means that climate change led to more risk of drought, less than 1, less, and it's a log scale. The observational estimate here shows an increase in drought, though with uncertainties. The CMIP5 model showed an increase in drought. Made 2 versions of the UK Met Office model, which for reasons I don't know, they chose to wait as well, and they just pooled all these uncertainties. The uncertainties encompassed 1. They couldn't reject the null hypothesis, and they said there was insufficient evidence to conclude that climate change increased drought risk. But I think we asked, insufficient for whom? If you were a water manager, you probably wouldn't be happy with that answer. So storylines represent the uncertainty space discretely and can represent these correlated aspects of risk, and this was the diagram that we came up with. And you can extend it into the human domain. We didn't analyze that, but as well as the local circulation and the drought and the heat waves, there was rising inequality, waste, environmental degradation, demand, and so on. So all of these kinds of concepts would be very natural in a risk management context. And especially the point there is that you can introduce intervention or decision points, which are important for adaptation. If you want to bring agency at the local scale, I think you have to give people a way to figure out how they might be able to make their own environment safer, and that'll be working in this space with the great process. So I'll just quickly mention that under the World Climate Research Program, they have core projects like Cloudfire and so on that have gone on Spark a long time, but they have lighthouse activities, and Regina and I lead one called My Climate Risk. Our idea is the idea of the project is to develop a mainstream, a bottom-up approach to climate risk, which starts from the decision context, enables the climate information to be brought into that context, and makes the climate information meaningful at the local scale. And rather than doing the usual WCRP thing of coming up with a science plan and then saying who can do the science plan, we've identified groups, communities of practice around the world, especially in the global south, and basically say our science plan is your science plan. Whatever you're doing is what we could consider important, and we're going to learn from that and work together. So it's really interesting experiment, and I'm quite proud of the fact that we've got engagement from around the world. Now, I do want to, I'll finish with a few FAQs, because usually when I go talk on storylines, these are some of the questions. So I say it's not about probabilities, and the first question is, well, what about probabilities? So I think, and you can't completely duck it, I think. So I think it's better science to acknowledge that some of the uncertainties are epistemic rather than just chance processes, and you don't want to give a sense of false precision. Wendy Park and James Risby have written a nice piece on that. If you want to treat the CMIP models as probability distributions. That's your right. And of course, IPCC tends to, in many cases, it's been moving away from that now. Models start to show that they're not, or the observations, I should say, are showing behavior outside of the model range. But if you want to believe that, you can believe that. It's a subjective probability, after all. Epistemic uncertainties are subjective. And I think actually a lot of people, quite a few people in my group, are working to try to provide a link between storylines and probabilities and make the causal networks probabilistic. So it is possible in theory. Now there's a question about subjective. I already used that word, but I think we throw the word objectivity around a bit too easily, and it's of course always seen as a good thing. But if the price of objectivity is to vary the subjectivity in procedural protocols, I would argue it's not a price worth paying. It's more important to be transparent. You can ask, aren't the number of storylines unlimited? And that's true, but if you focus on decision elements, you can quickly narrow things down. So I think that's not a serious problem in the end. And people always ask, how do you determine? We talk about plausible. It's funny, you say probable, and no one has a problem if you put a probability down, even though it may not have any basis behind it. Plausible seems to be a phrase that climate scientists don't really like, but I know the people that work with risk reduction and government advising, plausible worst case is a very commonly used term. In English, I don't know what they tell me what it is. So plausible is an important thing. It means worth worrying about, I guess you could say, but it must be a process of co-development with the user. If you're going to talk to a water company about the risk of a drought, they will have enough expert knowledge to have a good feeling for what's plausible or not. So for just to give an example, in the south of England, there's actually a lot of water shortages. There can be because there's so much demand. They get their water in the winter, as in the Mediterranean, basically, I guess. And the nightmare scenario is 3 dry winters in a row. They've had 2, but never 3. But they could have 3, right? It's certainly plausible. So to conclude, we have to navigate this cascade of uncertainty, to deal with adaptation. We have to connect to the decision space. Scientists want to say what will happen, but that's not the societally relevant question. The societally relevant question is, what are the consequences, the impact of particular actions under a situation of uncertainty? So actually, from our point of view, that's free, because it means we don't have to know what's going to happen. But we do need a language for expressing this plural conditional state of knowledge, and fundamentally we have to resist aggregation, because aggregation, I think, is an absolute, there's all kinds of problems. So I think the storyline approach is doing this by introducing the plural conditional, by resisting aggregation and the dynamic and thermodynamic aspects. It's not a rigid distinction, but it's a very useful one. I think also, I haven't talked about this, but if you link to historical events in their context, that brings a salience to the risk, which is well understood psychologically. Statisticians will say that's cheating because you're using people's emotions, but I don't know. That doesn't seem humane to me. It really happened. It wasn't just in a model. I think that's also important. And narratives are always important. Even a quantitative analysis always has a narrative at the end of it. And what I like about storylines is that the narrative is not contrived, built in. It's part of your analysis. But because it's a narrative, it gives you that emotional element, which is essential. But it's not just arbitrary. It's part of your analysis. And I think we need to disclose storylines of climate risk, considering all the evidence, best information we have, but interpret it not as a prediction, but as representing plausible